there's a few of you that have missed your intro to engineering interview with an engineer. So just make, I'm not taking late work on it, so I want to make sure that you guys keep track. This is one of those things that happen to you. You are responsible for your deadlines, and your boss isn't going to necessarily remind you that you have a deadline coming up. And that's because if you all were trying to keep track of me last week, it was next to impossible. Because Tuesday I was at a Women in STEM conference in Oklahoma City. Thursday I was at Stillwater doing a variety of things, interviews and a few other things. And this week has not slowed down either. So you will find that your schedule and your planner becomes extremely important. So speaking of planners, here's the deal. It's time to get those meetings with me about your planner. Starting from now until the 15th of November, you can schedule a meeting with me to go over your planner. You need to bring your planner. We'll come in and discuss it. Remember, I am not grading you on what's in your planner. It's more about what you used it for and the discussion that we're going to have associated with it. Your planner is one of your bigger point value grades that are coming up. If you haven't looked for your book report and your book and getting your books read, it's that time. We have this class. We have next week's class. I think we've got 3 classes before Thanksgiving break and then one after Thanksgiving break. So we're down to 4 classes left in here. And your book report is another one of the book memo is another one of the big point value items. There was lots of opportunity for extra credit. Not many of you partook. I'm a little surprised. The 2 ethics discussion boards, you had a great deal of opportunity for it. And I went through and I graded both of those ethics discussions. And we're going to actually talk a little bit more about the ethics situations that were in there, because that's really a critical part of what we do and how we deal with business is looking at that ethics. And just as a reminder, an enrollment opened for everybody on Monday. So if you're enrolling with me, the sign-ups are on my door. If you're enrolling with Dr. Knassen, I know he's got sign-ups on his door for over here. Over in Enid, I know Dr. Monroe has sign-ups on her door as well. For you guys over in Enid about your planners, I will be over there this Friday, weather permitting. And weather permitting the next 2 Fridays, so you guys can get in with your planners to talk about your planners. So that kind of gets us back on track. All right, so let's go back here and let's talk, because we ended up stopping when we were discussing ethics, and this is about where we got to our professional obligations. And that's really the crux of those 4 ethics scenarios that I had in the ethics discussion board is what are our professional obligations and it's not just engineers. Even though I am not a professional engineer, I do work under a code of ethics. I work under 2 different codes of ethics. One is the code of ethics for chemists, and one is a code of ethics because I am a registered environmental manager. And so we have our codes of ethics as well. And those professional obligations, whether you're a doctor, an engineer, a lawyer, they're not a whole lot different. There are some standards of practice that are different, but as engineers and when we're as professionals, there's not a terribly great deal of difference. That we're guided by our relations in terms of honesty and integrity. And if you guys remember, there was the one skit that they had done, they had staged the skit about billing in those ethics discussions that we took with regard to that discussion board. And the manager comes in and says, I need you to bill those hours because that project that you're working on is going to apply to the other project as well, so I need you to bill those hours to the other project. And the guy says, no, I did this project for company ABC, and that really, well, we got to come in under budget on company ABC. And those are actual discussions that you will hear. You will actually see those discussions that you will hear. And you can, and sometimes it's depending upon what exactly the work product is. If, for example, if you are developing an in-house tool that you are going to be using for the company, and it's going to apply to 20 different clients, maybe the company should pay for it. You know, maybe maybe those go on the hour of the company. If you actually are building it, it may be the work product associated with the company ABC. Sometimes it is a reasonable thing that you split the charges between two companies, because it's a tool that's being developed for both. It's exactly the same work. It's exactly the same thing. But neither company should bear the burden of the actual cost for what's going on. So you do end up with those debates a lot. And actually, that's one of the reasons I left my company that I was with, was we were having debates about how to bill the client and what should be billed to the client, partially because of what was promised to the client. And it was, yeah, we were doing work for the client, but the company promised them a certain work product, and we were supposed to be delivering that work product, not necessarily billing them extra hours to deliver that product. So that's a big discussion that you get, and there's lots and lots of gray area, and you have to really work and really look at exactly what's happening, particularly with regard to billing. I ate an awful lot of hours because I felt like that wasn't, it wasn't fair to bill the company or bill the client for certain things. So you end up having to deal with that a lot. So we're supposed to be the highest standards of honesty and integrity. Engineers shall strive to serve the public interest. Remember, if we're civil engineers, we're building bridges and roads. We're building wastewater treatment systems. We're building water systems. We're building systems. And when I first put up the ethics in the news, let's talk about PG&E and Edison, SoCal Edison. They've got a dilemma. PG&E and SoCal Edison have a huge dilemma. Their infrastructures are such that high winds can cause a power line to come down, and they could ignite a fire. The fire that's currently burning, that's caused in the North Sonoma County, PG&E had shut down. They had shut down, had started doing brownouts and blackouts, and the fire started about 6 hours later, and it looks like it was one of their lines that's ignited the fire. The big campfire last year was ignited by PG&E equipment, and so they are taking, one of the reasons they filed bankruptcy is because they didn't know how they were going to deal with the liabilities associated with the fire. But the question becomes, were they truly at fault? Can they predict high winds and high, those things are going to come into an area that may not be properly range managed? So is PG&E at fault? Then the ethical dilemmas of what was going on the 2 weeks before this last fire. You're not hearing them complain so much about blackouts anymore in California, now that the fires have started. The question then becomes, if you started listening to the news, well, they're turning off the power, and that's affecting lots of people that rely on electricity for their health care equipment. It's affecting food and food storage. It's affecting schools. It's affecting businesses. It's affecting a lot of different things. And is that right or reasonable? They were caught between a rock and a hard place because they were blamed for the fires the previous year, so they had to do something. So they had to start turning off power because of the conditions. So now you're sitting there going, okay, which way is right? And that's when we're talking about to serve the public interest, it becomes very, very difficult. And we have to look at it. Aaron Brockovich came on campus here about 3 years ago. And it was very interesting to listen to Aaron Brockovich. One of the worst speakers I think I've ever heard. It was really, really a dilemma. And you also have to sit through and look at what you're being told versus what's reality. So they were actually, one of the things that she brought up was a video of northern Pennsylvania, southern New York, eastern Ohio, associated with fracking, and how fracking had contaminated everybody's wells. And that people would light, I'm sure people have seen it. It was also an NC, or it was a CSI episode where somebody had come in to frack in Las Vegas, and they opened their spigot and they could light their spigot because the natural gas came through the spigot. Well, things you got to understand is that is a natural occurrence, by the way. We actually, if you go in Salt Lake City along the railroad, there are certain spigots that set about every 2 or 3 miles, there'll be a spigot right by the railroad. And it's a legacy from way back when. But those spigots actually look like our frost-free pump handles, except if you've ever been in the chem lab, you've seen the natural gas little vent that you get in the chem lab. At the top of these frost-free spigots is a little vent with a little cage sitting on top. And you're kind of going, okay, what is that thing for? Well, you turn on the water, and you let the water pour, and you fill up your coffee tin. You hit a lighter, and you ignite the spigot because you get natural methane gas from the peat bog that's sitting right there underneath it. So they fill up their coffee cup, they put their coffee container, they put their coffee pot on there, and it's actually so that the engineers, when the train was stopped, could actually make their coffee. And it was a result of the peat bog where the water was coming from, and that you could get the natural methane right off the peat bog, and you could actually do it. Well, all those stories in Pennsylvania and New York were actually true. People could ignite the water that was coming out of their spigots, and they've all blamed the oil companies for coming in and fracking. What nobody ever tells you is a lot of those things were there before one well was ever fracked. And it was those things were discovered when people started going in the environmental assessments prior to the fracking, and they actually discovered that people had contaminated wells from historic oil drilling done in the 1920s, not the current stuff. So you end up dealing with, okay, what is the public, the thing that's in there? And that's where it gets us, we shall avoid conduct or practice that deceives the public. Well, that's not deceptive, right? But if you're arguing with emotion, the people will never, ever be able to look at fact. And that's one of the things that really gets you. The Aaron Brockovich thing came up is because they were trying to get clients associated with the earthquake damage associated with fracking. And so you're going, okay, all right, I get it. Injection wells cause, there are correlations for some of our injection wells that we do get man-made or man-induced earthquakes. Okay, so yes, if in certain areas of the state, you're actually seeing damage from the earthquakes. Particularly in northwest Oklahoma City, where you are getting damage. They did have chimneys fall. Well, if you start looking at it and you look at the strength of a 2.0 or a 2.5 earthquake and a chimney falling down, we got a little bit of a problem. Is it the earthquake that caused it, or was it shoddy construction? Because I'm sorry, if a 2.5 earthquake is going to take down a chimney, I'm pretty sure some of our Oklahoma winds are going to take down that chimney too. And so we have some issues there. So the question is, who are you blaming, and which engineer is at fault? Is it because we didn't construct the house properly? Yeah, probably. And then the question is, did we really not construct the house properly because of earthquakes, or did we not construct the house properly because of wind damage? So that's one of the things that we have to look at. And that's going to get us into this next stuff that we're headed into. We're headed into fundamentals and talking about measurement and double checking and peer review. And so the next several chapters in the book They break it up in terms of fundamental measurements. They break it up in terms of types of units that we're going to see. And so it's just to kind of get you some exposure on what you're going to see in your upper division classes. But even if you do everything correctly, everything that's out there, and you've done it to your best of the ability, there's still going to be times when things don't work out the way you want them. And then it's time to fess up and be honest about it and not do a cover-up. So engineers shall not disclose without consent confidential business information concerning the affairs or technical processes of any former client or employer. That was one of the other ones. There was a discussion of, okay, the guy did parts 1 and 2, now works for the state. Is there something that he can say or disclose that associated with it? He does have a conflict of interest and has to declare that conflict of interest. So we do have to worry about conflicts of interest and the apparent conflicts of interest. There may not be one, but there may also be one. We shouldn't be influenced by our duties by conflicting interests. That's what we were talking about already. Engineers shall not attempt to attain employment or enhancements by untruthfully criticizing other engineers or by other improper or questionable methods. So, you don't slam other engineers. But I will tell you, you can look at other engineering reports, and when you are evaluating your own work, decide whether or not you would have paid for that work. I have seen many, many engineering reports that I'm so glad I didn't get that one because I wouldn't have paid for that. And that's one of those things, when you start looking at it and when I start talking to you about evaluating your memos, think about it as if I'm the client and would I pay for that? And when you start getting into my statics class, you actually write engineering reports, and I will tell you, would you as a client want to have that report presented to you? And that's a lot of the different things that are looking at what we look at. Engineers shall not attempt to injure maliciously, falsely, or indirectly the professional reputation or practice of other engineers. Like I said, I had a disagreement with my boss. My boss wasn't necessarily wrong. We just didn't see eye to eye about it. And that was, and he's the boss. So that was, he wasn't incorrect. The client deserved to pay for the work. I just felt that we had promised something. So it's not that he was incorrect. It's not that I was correct. It was just a difference of opinion between the two of us. And that told me it was time to go. For me, that told me it was time to go. And it's not that the company was doing anything wrong. I just felt like he had promised the client something. And that's just that's where you end up and you look at different things. Not that was incorrect. Engineers shall accept personal responsibility for their professional activities. We shall give credit for engineering work to those whom credit is due. And this is an interesting one because we see this a lot, and it is a tricky thing, and it's part of culture. I have always felt that laboratory technicians should receive credit. Technicians on the job should receive credit. Some companies say it's only the senior professional that gets the credit. That's always been an issue. If you think about the discovery of DNA, we all know Watson and Crick had the DNA, but people leave out the laboratory technician who actually did the X-ray crystallography that showed this stuff. She should have been on the Nobel Prize as well. But historically, laboratory technicians were not credited and not put on patents. So there are things that are in there that you have to also, we've seen change over time in terms of culture. So that's one of those things. The Engineer's Creed, it's out there depending on which society you're in. It's in there and it's there. So that's the Engineer's Creed. Some other definitions that we have to deal with. Academic dishonesty. We have an academic dishonesty policy here at NOC. It's out there. Things that kind of get into the gray areas, Chegg. Chegg can be a helpful tool, or Chegg could be a source of academic dishonesty. It depends on how you use it. If you're using it to help you figure out solutions to the problem and figure out the stuff, or are you using it just a straight copy for your homework? I mean, there's two different things. Everybody will see in my office, I have the old version of Chegg, before Chegg was Chegg. I have these big, massive volumes of standard problems and their solutions. They're called problem solvers. So it's a place where you can go to find a similar problem to look at and similarly work it out. It's the same thing as we're working in teams to get solutions to the problem. I have no problem with people working in study groups. I have no problem with people working in Chegg. I have no problem because it's a tool. It is an absolute tool. I have no problem going to the internet and seeing what's out there. The question is how you're using that tool. How you're using that tool. And we will talk, here the other day I published the test for a makeup, and I actually published the answers with the test. Okay? I inadvertently did that because I have not been feeling well, as most of my students will tell you. So I've not been at 100%. I still haven't figured out what I'm going to do yet. Still not going to figure out what I'm going to do yet, but there's an issue there. Plagiarism. This is when you don't give credit for where credit is due, and I will tell you this is a struggle. Okay? I will tell you this is a struggle. So things like Turnitin, things like Grammarly, things like a variety of places will look at plagiarism and will give you the percentage of plagiarism that is in your memo. The real trick is there's only a certain number of ways to say certain things. And so now you're getting plagiarized. You're getting plagiarism paragraphs that you're going, well, how else is somebody going to say the dog was brown, That would be listed as plagiarized, and my plagiarism checker will actually tell you the reference where they found it. Well, the dog was brown. I don't necessarily think that that's a plagiaristic sentence unless you're quoting it from a poem and you're using it as a poem. You end up, so we actually now have probably a lot more difficulty with this than we have historically. Because there's just so many ways that, when you define certain things, if you're defining it in your own words and there are 1,500 dictionaries out there, it's likely that you're going to find a dictionary that says it the exact same way. So you've really got to be careful about how plagiarism is done, and you've got to be careful about how you reference or how things are referenced. So that's where you give credit where credit is due. If you found it, and you're even if you're using your own words, but the ideas are out there, you need to be referencing it. Conflicts of interest, normally we think of monetarily conflicts of interest, but there are other conflicts of interest as well. That's why when I actually have to fill out for certain things, family members, who my family members are, one of the things I had to do here recently was for the National Science Foundation grant. I had to list everybody who signed my dissertation because if they were a reviewer, it could be a potential conflict of interest, which was really funny because, it's more done for current people than it is because all but one of my thesis committee is all retired. They're not going to be reviewing NSF documents, especially not in the areas where we were applying. But it's something that they have to identify for potential conflicts of interest. Contracts. If you have a contract, you have to know what's in the contract. And that really gets you in terms of who owns intellectual property and where that intellectual property is, and then just your professional responsibility. We have, my professional responsibility is mine, my reputation is mine, and that's why we got into a discussion with my boss. Actually, what I ultimately told him is if he wanted the client to pay for it, he needed to have that discussion with the client. Because it was my professional responsibility. I felt it was promised, And I wasn't going to go to that client and ask them for money for that. And that's essentially where the disagreement came. And if he felt that we needed to bill it, then that was a discussion he needed to have with the client, not me. Because that was how I felt about it, and how my boss felt about it were two different things. And that was just how we deal with it. So those professional responsibilities. So those are things that we really start working with and start dealing with as engineers. So now let's talk about what's happening in the next one. So here's what we're going to do. Let me go back here because this is a. So down here, week 11, because I have some hidden weeks for you. This is homework in chapter 6. It's through Blackboard, and because we're going to start talking about fundamentals and looking at it. And our book is really, really a good reference, by the way, for when you start going into the upper division classes. For some of you that you're going to start seeing it when you get into Engineering Physics 1 next semester, start seeing it when we get into thermodynamics, start seeing it in other things. We're gonna kind of whip through these chapters. So again, you've got your expectations associated with it. The discussion board this week, because this particular chapter is on measurements and things like that. So if I go here to my discussion board, it's on tiny mistakes that led to a disaster. I've given you a couple to start. The Mars orbiter being one. You know, here's all this work. We get the orbiter to Mars and something goes wrong. Hubble telescope is another one. It essentially needed glasses because there was a mistake. And then there was another one that totally missed the planet because somebody was using English units and somebody was using metric units. They weren't on the same unit scale. And so when you think about those, that's a $125 million project that just went down the tubes because of a small mistake. And that's why we did that. So this discussion board is worth 25 points. So you guys, we've got 25-point discussion boards in there to kind of help get more points back and get us going. So the next few chapters, what you're going to end up with is not memos. You're going to end up with some homework in Blackboard associated with it. And this one was we're looking at fundamental dimensions and units, systems of units, and conversion and dimensional analysis, because that really helps us. We'll talk a little bit about significant figures. Hopefully between chemistry and physics, we've talked about significant figures enough that you sit out there, and components and what we get. So concepts that we're going to go through and that everybody should know. What are our fundamental dimensions and units? Things in length, time, mass, force, temperature, electric current, and energy and power. Those are going to be fundamental units that we want to look at. And we're going to start out with our length, time, mass, temperature, electric current, amounts of the substance, and luminous intensity. We end up using length, time, mass to derive other units a lot. Length is going to be like in feet and meters and centimeters. Mass is kilograms, slugs. Times in seconds. Luckily for us, it doesn't matter whether you're in conventional units or not. Time isn't still in seconds. Time is also strange because time is one of the ones that does not go backwards. Length, if I have a negative, it tells me direction. Temperature is an interesting concept. It allows us to compare things. Electric current is in amps, amounts, and luminous is brightness. Okay, luminous is brightness. So units are used, they're physical quantities. It makes it so that numbers have meaning. Numbers have meaning. Is it 3 feet? Is it 3 kilograms? Is it 3 seconds? Is it 3 hours? Is it 3 books? Is it 3 moles? Numbers have units. If there's not units, we don't necessarily know what you're talking about. And we do appropriate divisions of physical dimensions. So this is always entertaining. We use units to group them together so that they have physical meaning, and we use it so that they're easier to work with. So depending, I like this one, 19 years versus 612 million seconds. All right. The other thing is look at the precision of that. If I really want to know how many seconds old I am, I'm going to be down in the weeds. And sometimes we need to be down in the weeds. Sometimes we don't. It's an interesting concept of time, by the way. I talk about time being an interesting phenomenon. Why does time seem to go faster as you get older?
Entropy.
Do I?
I would say entropy.
Entropy?
Yeah.
Oh, that's an interesting way of putting it. Well, let's think about it. When I'm 5 years old, 1 month is 1/60th of my life. If I'm 50 years old, 1 month is 1/600th of my life. So when we're younger, think about your lifespan in relation to time. So when you're 4 and Christmas is coming, 8 weeks is interminable. When you're 72, 8 weeks is just around the corner. And part of it is just the percentage of your life that it is. So that is it's a different way of approaching time. Now time is weird in and of itself, right? Because we all know that we can set a timer, and depending on what we're doing, that 10 minutes can fly by, or that 10 minutes can seem like an eternity. And so there is a weird perception of time that we have to deal with. But time is a strange being. The other thing about it is how we count time. Depending on which text that you like to go back, remember Noah supposedly lived like 900 years, right? So let's just take how many years. So there's actually a person down at OU that actually wrote a paper discussing time in ancient texts and why people may have lived 900 years. Because if you start counting time, if we are primitive man and we're counting time, we're starting to look at cycles. First cycle we look at is the sun comes up, the sun goes down. Second cycle we look at is the sun just comes up every day. Third cycle that we look at is the moon comes in the same place every 28 days. So now we're talking months. Or then we get into seasons. If we're in a temperate zone where we get 3-4 seasons, we can start counting in seasons. So we can look at how many seasons somebody has. If you start looking at those terms and you start looking at what somebody might call months versus years, and you put them on the same scale, guess what? Noah lived to be about 60 years old, depending on on the way, or at least his hypothesis. So depending on how you're counting time makes it for a very interesting approach, and calendars become extremely interesting. I actually have a piece that says, does anybody know what day it is? Because if I'm on the Gregorian calendar or the Julian calendar, we're about 14 days off. Depending if I'm on the Hebrew calendar, we're at a certain year. If I'm on the Chinese calendar, we're on a different year. If I'm in the Muslim calendar, I'm in some other different year yet. And then probably the most current calendar that we would be the youngest on is the French Revolutionary calendar. They decided to make their own calendar after the French Revolution, and it's out there. So you get some interesting calendars to start looking at where we are in days-wise. So we have several systems of units. In physics and in chemistry, we're using SI units typically. We also have the British system of units, and then we have U.S. customary units, which is actually a mix of the two above. Kind of an interesting piece. There's also nominal versus actual. If you ever take a 2x4 A 2x4 isn't really 2 inches by 4 inches. It's something like a 1.75 inches by 3 inches and some odd. So we have these nominal units that we work with. 4x8 piece of plywood, nominally 4 feet by 8 feet. Not necessarily exactly 4 feet by 8 feet. So we end up with different units there. SI units the most common. That gives us meters, kilograms, amperes. And we have the various standards that we go. And then our fundamental unit of length is a meter. And it now everything is defined by a physical constant of the universe. Kilogram was the last thing to not be defined by a physical constant of the universe. It was actually a physical object at one point in time.
That?
Huh?
Did they actually go through and change that and take it from the actual physical item and turn it into the? Were they going to use like the amount of electrons in something?
Yep. They've actually changed it. It's been a 4-year process, and I think the final year of it was last year or this year. So we've been going through a change because all the kilograms were losing weight.
So does that mean our textbooks are going to change like next year?
No. The big people who had the big discussions about it were analytical chemists that were working in things that were like 10 to the minus 6, 10 to the minus 8 for standards. Most everything it won't affect too much because of what they went back to do the definition. It really doesn't affect it a whole lot.
So really it's just going to affect the precision once you get down to the electron structures.
Yep. It affects the precision. Yeah. And this one says it's still the prototype. No, they changed it. And it's been in the process of being changed for a while. Second, this is I love this one of the CZ133 atom. So we go back to a physical context there. Ampere is the current that goes across. Kelvin is our fundamental temperature. We go off of Kelvin. Celsius and Fahrenheit are referenced back to Kelvin now, so that we end up with that. And then we can convert. And I never remember the conversion for Fahrenheit to Celsius. Mole is the substance that contains as many entities as there are in 0.12 kilograms of carbon-12. So that's how many atoms are in carbon-12 that we end up with our moles. And luminous intensity are in candelas is for our luminous. So we get the prefixes if we're in SI units, and hopefully most of us know gigas in there. We get some good ones. Gigas are 10 to the 10th. So depending on which ones, we do have yadas and yaktos. So you can play with the various ones that are out there. Derived units are going to be like meters per second squared for acceleration. We get momentum, doesn't have a special unit. It's going to be our kilograms, meters per second. But then we get things like newtons, which are kilograms, meters per second squared. And so we can derive it into a newton. A joule is a newton meter. So we derive into another unit. And then you can play with a bunch of them. Now, this is a handy table, particularly when you get into physics 2, because it's hard to remember what an ampere is. It's hard to remember what a volt is. It's hard to remember what an ohm is. And then you start getting into Teslas and a few other things, and it gets a little more difficult. So it's nice to have these kinds of tables. What the tool that you have on the internet is called the Engineering Toolbox, and it also has tables like this, which is a really handy reference page for things that are there. Gravitational units. The slug is for mass. Remember, pounds and newtons are force. Slugs and kilograms are mass. So we end up with different things that are out there. There is another form of temperature. This one actually gives it to you, Rankins. We do see those occasionally, and we run across them occasionally, that Rankins are out there as well. Fahrenheit is our temperature. Now, Fahrenheit actually was based on a 0 to 100 scale. It just wasn't the same 0 to 100 scale that Celsius used. 0 was the coldest thing that Fahrenheit could get to, which was an ice alcohol bath. And body temperature was his 100, even though he was off. But that's how he derived his scale. He went for the coldest thing that he could reproduce and for something that he felt like could be easily reproduced from lab to lab. And that's why we have, it goes from 32 degrees to 212 instead of 0 to 100 in the Celsius. And the reason Celsius didn't catch on is he initially had his temperature scale backwards. He used 100 as the freezing point and he used 0 as the boiling point. Not that it was wrong, just wasn't an easier convention to use, and so people used Fahrenheit's convention first. English, or our customary units, pretty much the same as the British units, but we have a little bit of difference there. So we've talked about SI units versus customary. Things are just slightly different that we have to work out. And we get things that we use in everyday use. Film is in millimeters, even though we're in the U.S. system. So like I said, U.S. customary units are kind of a mix. And it's really important that you guys get a set of references in your head. So that when you're out in the field and somebody says walk off 100 meters, you know how far that is. Because you may not necessarily have the measurement device to get you there. You know, somebody says take something a foot away, you need to have a good idea what 12 inches is. You need to have a good idea what 100 meters is. You need to have a good idea of what feels like 1 pound, or what it looks like to have 1 milliliter of water. So those things, you really have to have that for when you're in the field, that you don't necessarily have a measurement device with you. So, I mean, it really does help because you're looking at it and your toolkit is basically what you have on your person, or what you have in your briefcase, or what you have in the trunk of your car. And sometimes you're 50 miles from nowhere and you have to make adjustments. Oh, okay. So unit conversions are huge and they will save your hide. They will absolutely save your hide. They will save your hide when you start getting into the upper division classes, because it's going to tell you whether you've multiplied or divided correctly. It'll tell you whether or not you've rearranged your units correctly. It'll tell you if you've lost a square somewhere. It tells you a lot. Unit analysis really, really helps you out. And it saves your hide a lot. You want to make sure you have unit homogeneity. Things you can only add links to links. You can only add time to time. You can only add velocities to velocities. It helps you out. And then we do numeric versus symbolic solutions. There are times to do numeric, there are times to do symbolic. And a lot of times what you want to do is you want to do your symbolic so you can put it in your Excel spreadsheet so you can change your variables. Or you could put it in your computer program so you can change your variables. So you want to have the symbolic solution, particularly when you're doing things over and over again, so that you can have it easily there and that you can easily substitute with different data. But sometimes when you're working for a back of the envelope, it's easier to go ahead and put the numbers in, so it makes it more straightforward. So you have to make a choice which way you're going to do it. Have to make a choice. And we can do numeric solutions. Significant figures, depending on the convention and depending on where you're at, will depend on our convention. Significant figures tell you the precision of the measurement, and it's interpolative, so it also tells you where the error is in your measurements. And then you have to deal with, so we've got lots of things that are out there. 3 significant figures, hopefully everybody remembers which ones are placeholders. The .00 in front of the 125 are placeholders. all digits used in scientific notation are significant, and we end up having to deal with our rounding, and usually we will round so that the last number is even. So we're rounding up half the time and we're rounding down half the time when we hit with the number 5. I'm going to stop there, and we will get back together next Tuesday. You've got homework out there, and we will see you all at some point.